There are 13 questions on Exam 2 for this course. Exam 2 focuses exclusively on your derivative rules. And on this Exam 2 with 13 questions, you can expect about 8 of them to be multiple choice, and the rest, which would be 5, are where you type it out. If you didn't do so hot last time on the type it out questions, maybe you should mentally prepare yourself to have to do that this next time. So let's work some examples that I believe will help prepare you for those 13 test questions. Okay, so let's start off, I guess, kind of easy. Let's make sure that we understand that you can differentiate term by term. You can differentiate term by term. Maybe the question is something like this. Find h prime of 10 if h of x is 4 times f of x minus 5 times g of x. Okay, they give you the definition of h, but then they also come over here and say, well, f prime at 10 was 2 and g prime at 10 is 3. Then this is just like a homework style question. And when you want to find h prime, you have to differentiate term by term. So we take the derivative of this, and we take the derivative of this, and then whatever that is right there would also go between our two derivatives. Not only does this check that we know how to differentiate term by term, it also shows us that if you have, I'm running out of letters here, if you have a constant times a function, and then you want to know the derivative of that function, it's just the constant times the derivative. The constant just comes out front, is how I like to say that. So this will be nothing more than 4, and so I kept my 4, and then it's times the derivative of f. Well, that's f prime of x. And then minus the 5 times the g prime of x. Well, now you just get to drop in your numbers. So that's going to be 4 times 2 minus 5 times 3. And you can compute that as 8 minus 15. So it's minus 7. And hopefully you see that as one of your answer choices. Okay, so everyone has that example down pat. What about where you have to find the derivative of a function and it needs the product rule? So here I have a function and it's going to need my product rule. How do I know that? Well, because I'm the one writing the question down. So 10x to the 11 and then times e to the 2x. Okay. So you're looking at this function y, and what you should really be seeing is that you have a constant way over there, and then over here you've got these two functions being multiplied. Okay, this is what y looks like. So dy dx is the name of a derivative, It's the name of a function. It's the derivative of y. And that function would be, okay, well, here's my constant. It comes out front. Now I'm free to deal with this product of two functions. You should take the derivative of the first times the second plus the derivative of the second times the first. Now this is a multiple choice test for 8 questions. You need to be prepared for the idea that the thing that you've got here is not one of the answer choices. You will either have to distribute the 10 or you will have to factor out some e to the 2x and some x's. If I distribute the 10, I'd be getting 110 x to the 10th e to the 2x plus 20 e to the 2x x to the 11th. Right? That's what it would look like if I distributed. If I had to factor it, then you can factor out an x to the 10th e to the 2x. So I would be getting 10x to the 10th e to the 2x, and then the stuff that's left over is 11 plus 2x. Okay, great. I actually prefer it when it's factored, but you should be prepared to see either one. Here's another example. What about if I gave you the function 1 over the cube root, 1 over the cube root of x cubed plus 5x squared plus 2x. 1 over the cube root of all this stuff. Well, you are a calculus student, so automatically you hate the radical symbols. They are arcane. They are not helpful. You, as a calculus student, much prefer the rational exponent. Here's the fact. The fact is that the nth root of something is just that something to the 1 over n power. Take that fact together with this other fact that a 1 over something to an exponent is equal to just that guy with the sign of the exponent switched. Here, this is how I usually write it. I will usually write it like this. So that way each side looks like a fraction. Look at how the thing switched to the other side of the division bar. This guy moved to the other side of the division bar, and when that happens, if I want it to still be equal, then all I gotta do is switch the sign of the exponent. Okay, so then together with these two facts, you got a handle on this problem. This would be nothing more than, well, here's my object, here's my star. My star is x cubed plus 5x squared plus 2x. It's that thing under the radical, but instead of being to the cube root, it's going to be to the minus 1/3. You can see that it became a 1/3 because of this fact, and it was minus because of this fact. Well, now I've got a writing of f that I like. I know how to do this derivative. It just needs my power rule and my chain rule. So f prime of x, I have my, well, let's make some writing. So this function was called f. I don't like that anymore. I'm going to change it to h. because f is going to be busy over here. F of star is the function star to the minus 1/3. And g of x is going to be that thing on the inside, x cubed plus 5x squared plus 2x. Now all I need is f prime and g prime. I'm literally going to multiply them together, and that's my answer. With the only caveat that g of x is what star is going to be. Okay? So f prime of star right there, well, that's just a power rule. So you get a minus 1/3 star to the minus 1/3 minus 1. So that's minus 4/3. And then I'm running out of room. G prime of x is 3x squared plus, well, hopefully you see what g prime is. I'm out of room. So we're going to write it down right here in just a second. But whatever g prime is, we're going to multiply g prime times this. Multiply, not divide. So h prime of x has got to be f prime of star. So that's a minus 1/3, and then here's my star, and then to the minus 4/3. Okay, super. And then it's times g prime. Well, g prime is 3x squared plus 10x plus 2. Great. Now let me backtrack and replace this star with g. And g is the x cubed plus 5x squared plus 2x. Great. The derivative is done. The answer probably will be just in that format right there. Okay, let's say now I want to do, let's see. Let's say now I want to do, we need to write equations of tangent lines. You just can't get away. I mean, no calculus student of any sort is going to be getting away with completing the course without doing equations of tangent lines. All right, so let's say that I have a function. Let's say my function is 5x squared plus 9x. Okay, I like that one. And I would like to find the equation of the tangent line when x is 1. So we're going to find the equation of the tangent line when x is 1. So this guy here is some kind of parabola, and it's making a graph looks like this pretty much. And when x is 1, we want to know the equation of this line. Okay, then we need the derivative of f, because the derivative will be able to tell us what the slope of the tangent line is for any value of x. And in this case, they're wanting to know about it when x is 1. So we would have f prime of 1 being just 19. we are also going to need f of 1, because the point on the curve where that tangent line meets the curve is at this point. And the only way for us to construct the line whose slope is 19 and goes through that point is to know what f of 1 is. So that's going to be 13, because it's just 5 plus 9. Okay, you now have everything you need to write the equation of your tangent line. All tangent lines have this equation. All tangent lines have the following equation. Y minus, let's say that this is at the point W comma f of W. Then it's y minus f of W is equal to f prime of W times x minus W. It seems confusing. I promise it's not. This is exactly y equals mx plus b. Because if we were talking about the if they wanted the tangent line at the spot where the curve crossed the y-axis, then look, this would exactly be y equals mx plus b, because it'd be y minus 0. Sorry, I've goofed this up here. It'd be y minus b is equal to, and then I'd have f prime of w. Well, gee whiz, that's the slope. And then it'd be times x minus 0. That is the same thing as y equals mx plus b. It's just that this is a more general form of y equals mx plus b, because y equals mx plus b is the slope-intercept form, where you would need to know the point 0 comma b, but we don't know that point right now of this line. But we've got everything we need to just drop it into this equation, and we are done. All right? So we would have y minus f of w. Well, f of w is 13. That's going to be equal to f prime of w, which is 19, and then times x minus 1. And you can leave it like that. That is the equation of the line. If you need to put it in slope-intercept form, then you would have to distribute and solve for y. Let's say instead this time, we wanted to know where is the tangent line horizontal. All right. And I've got some function. I don't know what it is. Let's say we don't know what it is just yet. But you've been given the derivative function. Maybe the derivative function is something like, 5x times x plus 2 cubed times x minus 3 to the 1. Or we'll say squared. That's fine. So you f of x is some crazy function, and when you took its derivative, you got this, and lo and behold, it got factored beautifully. Now, you need to tell me where the tangent line is horizontal. Well, look, y'all, that just means that this expression would be 0 for some x. So you are supposed to consider, where does this thing be 0? Now, a lot of you will get that, okay, it's going to happen when x is minus 2. And a lot of you will get that, okay, it's going to happen when x is 3. And then for whatever reason, a lot of people just throw this away. Don't throw that part in the garbage. This is just as an important part as the other parts. In the same way that if a minus 2 goes right there, you get minus 2 plus 2 being 0. If I put 0 right there, then it doesn't matter what the rest of this says, because it's 0 times a bunch of stuff, which will be 0. Therefore, you get a tangent, a horizontal tangent at minus 2, 0, and 3. And before long, you will be making your number line drawing. And here's your minus 2, and here's your 0, and here's your 3. And that was each of the spots where the function was 0. And you'd be trying to figure out what's the sign of the function in any of these intervals, right? It would be negative in this interval, and it would be, no, I'm sorry, it wouldn't be. It would be, so if I used a test point of like 1, then it would be positive in this interval. And it's positive in this interval, and it's negative here, and negative here, I believe. Anyway, this is what is on the horizon. But this would be for f prime, and so we know our function is decreasing in both of those and increasing in both of those. All right. Let's see what else we can do. Well, you're gonna need to know so you're gonna need to know your product rule. You're gonna need to know your chain rule, and to a lesser extent, even to the point of being eliminated completely, is that quotient rule. Nobody likes the quotient rule. It's totally replaced by the product rule and the chain rule. For example, let's say I give you a function defined abstractly. I say my function is just f of x over g of x. Okay, great. Well, maybe you know the quotient rule and can plot down what the derivative would be. I can do the same thing without knowing the quotient rule, because this would just be f of x times g of x to the minus 1. Remember our fact. In this case, n is just 1. So up here it becomes g of x to the minus 1. Okay, well, super. Then I can take the derivative of h. It would, and all I need to know is the product rule. There's no sign to mess up on the product rule. You know, you're not going to get that minus sign in the wrong spot. It's the derivative of the first times the second plus the derivative of the second times the first. Well, my minus 1 is going to come down, and then it would be times g prime to the minus 2. Sorry, I goofed this up. The minus 1 comes down. I'm running out of room, so it was a plus, but it's times minus 1, so it will be a minus. And then, so there's my minus 1 coming down, and then it's going to be something to the minus 2, and then times the derivative of that something. That's just chain rule. But the thing that goes here is g of x. And then to finish off your product rule, it's times the first. But if you look carefully, I know I didn't write it all that great. This is the quotient rule. This is the quotient rule. You can always factor out the stuff whose exponent is closer to minus infinity. So a g of x to the minus 2 is going to factor out, and then you would be left with f prime of x times g of x minus g prime of x times f of x, and this is the exact quotient rule. Either way you want to do it's fine with me. When it comes to actually doing functions that are defined, I prefer to use this style. And you know, maybe they'll give you like a bunch of numbers. They'll say like, you know, find, you know, they'll say find h prime of, I don't know, 0, and find what that is, given that you know what f prime of 0 is, and given that you know, I mean, we can just say f prime, I'm going to make up a problem. F prime of 0 equals g prime of 0 equals f of 0 equals g of 0, and they all equal the number 1. They all equal the number 1. Well, then your answer here would be 0, because it would be looking like 1 times 1 minus 1 times 1 over 1 times 1. That's 0. Okay. Let's see. Always on our mind, or not always on our mind, but in the back of our mind is this easily forgotten, or easily overlooked, not easily forgotten fact, is that the derivative of a constant is 0. This makes perfect sense to you because, after all, a constant function is a horizontal line. Maybe this is the constant function y equals to k. That means that on my in my coordinate system, that y value right there is k. In fact, that ordered pair is 0, comma k, and any ordered pair on this line looks like something dot k, something comma k. All the points are looking like something comma k. And what is the slope of this horizontal line? It is 0. And you know that one of the interpretations of the derivative is the slope of the tangent line. So it would tell you that this is just what y prime is. Y prime would have to be 0. Okay. You are going to need to discuss using your power rule. Maybe this is the name of it. I can't remember for sure. It's just that rule so that the derivative of an x to the n looks like n times x to the n minus 1. I guess that's called the power rule. So maybe your function is, it shouldn't be too challenging, but it's going to have, you know, multiple pieces. Maybe it's 5x squared minus 8x to the fifth. Well, then you have to differentiate term by term using this power rule, right? You are looking at that as you would say, I'm going to pull my constant out and then worry about differentiating the part that explicitly looks like an x to the n. Okay, well, so then you'd have 5 times 2x to the 2 minus 1, which would be 1. And since the exponent is 1, you don't write it. And then over here you'd have your 5 comes down, and then it's x to the 5 minus 1. But 5 minus 1 is 4. And, whoop, this is not completed yet, because you would simplify it to say 10x minus 40x to the fourth. And if you can go from here to here, by all means, do it. Like I said earlier, quotient rule stinks. If there is a way for you to avoid using it, and there always is a way to avoid using it. If there's a way for you to avoid using it, do it. Do it. Maybe the only exception to wanting to avoid it is like this type of problem where they just give us a bunch of numbers and they say, hey, we know what all these numbers are, so tell me what h prime would be. Well, then maybe it pays to know the quotient rule, so that way you're just not deriving it again like I did here from the product rule and the chain rule. But it really makes no difference in either case. This fact remains, and so if you have a function that is looking like a quotient rule, then maybe you should think twice about whether it really is a quotient rule. Let's do it like that. Not only does this not need a quotient rule, you don't even need a product rule. What you need here is a rewriting of f using your algebra. When you look at this right here and you are seeing a single term in the denominator, instantly you should be thinking that thing is really 3 fractions, all with the same denominator, being added together. That's what that is. That's a sum of fractions, all with the same denominator. But then each of these guys gets simplified on the top and bottom. You can make some cancellation. So f of x is really just x to the 4 minus 7. Well, that's minus 3. Plus 3 times x to the 3 minus 7. Well, that's minus 4. Plus 4 times x to the 2 minus 7. That's minus 5. This is calculus style. This is how we like to look at our functions in calculus. This is a pain. This is what we love. We love it because we know the derivative rule to get this done in a hurry, but this thing looks nasty. Now it's just a matter of banging it out. Minus 3x to the minus 4. It's minus 4 because it's minus 3 minus 1. And then plus, you're going to have your 3 times the minus 4, because the minus 4 comes down, but 3 times minus 4, that's just minus 12. So it's minus 12x to the minus 4 minus 1. And then same thing here, you're going to have a 4 times a minus 5, so that's minus 20. X to the minus 5 minus 1, that's minus 6. And this is your answer. All right, I also want to stress to you, that stuff like this, e to the x squared, right? I didn't put any parentheses. This explicitly means e to an exponent whose exponent is x squared. This is what it means. You cannot say that this is e to the x squared, because that guy would just become e to the 2x, a very different object. Clearly, e to the x squared is not e to the 2x. Right? So e to the x squared does not mean e to the x and then it's squared. If I wrote e to the x in parentheses and then it got squared, then I could easily simplify it to this. No problem. You had problems like that in your homework where it was like 3 to the x squared. Well, that's just 3 to the 2x. Okay, but it had the parentheses. This would not be the same thing as 3 to the x squared, because what that really is 3 to the power of x squared. So I stress all that to you because now I want to do some derivatives involving that type of stuff. So let's say you had a function that was how about 3's looking good. Let's do 3 to the x squared, what we were just looking at, and plus, I don't know, let's say e to the, make it really confusing for you, e to the 3x squared. There's a lot of 3's, x's, and squares floating around. How are you going to navigate this? Well, the first thing I'm going to do is simplify this part right here, because that, like we just covered, says 3 to the 2x. And the rest of it cannot be simplified. It's e to an exponent, and that exponent is 3x squared. So this is the function I want to look at. All right. F prime is going to have to be, all right, so I want to take the derivative of the 3 to the 2x. And we are knowing that if I have some b to the f of x and I want its derivative, then this is just going to be f prime of x times b to the f of x times the natural log of b. It exactly coincides with how you do this derivative, except for that the natural log of e is just 1, so you don't have to write that part. So this is nothing but the chain rule. This right here is nothing but the chain rule. In fact, I shouldn't even write down special rules like this, because you should only be using the general rules that you know. It keeps your list short. You know, I mean, in this homework, or not in this homework, in this review, I've used the rule about x to the n, product rule, and chain rule, and there aren't any others that you need. This is it. this function here, the 3 to the 2x, is looking like something to the 2x power. Or excuse me, I misspoke. It's looking like a 3 to the some kind of something. That's the big picture on this function here. I would want the derivative of this. Here, I'm hemming hawing around because of this saying f. I shouldn't even do that. Let's call this guy h. Okay. Now I want to just explicitly write out what my f would be, right? F of star is going to be 3 to the star. G of x is just 2x. That only will apply to this one here. Okay, I'll underline it in blue so that the colors correspond. This one here has an f of star, which is e to the star, and it has a g of x, which is 3x squared. Okay, all of this does not need to be written down in a written solution. This is just a guide to help you. F prime of star is just like e to the x had derivative e to the x, anything to whatever has derivative that looks exactly like it how it came, except for you have to multiply to the natural log of the base. If that had said e to the star, I would have multiplied by the natural log of e, but that is the number 1, so you don't need it. G prime is 2. Okay, I've got everything I need for that one. Moving on to the other one. F prime of star is e to the star. G prime of x is 6x. I'm ready to write down my answer. H prime of x has got to look like f prime of star times g prime of x. That's the chain rule on that part of the function. And then I'm going to have to add the green ones, which is f prime of star, the green version, times g prime of x. Great, so I've got like a template going for you here. This derivative is the chain rule on this part of the function. As you can see, you are literally just taking this times this. You're multiplying them together. So h prime of x has got to be 3 to the star natural log of 3 times 2. It's always a safe bet to put some parentheses around your g prime, even if it's just this number. And I'm going to come back and replace the stars here in a minute, because I'm on a roll right now of just dropping stuff in, boiling stuff down to easy derivatives and plugging it in where it goes. So up next is f prime of star, that's e to the star, and then times g prime of x. G prime of x goes here, that is 6x. Wonderful. If I can replace those stars, I will have the final answer. So what does star have to be though? Star is g of x. Star is g of x. So you come back. Now when you get good at it, you can just do it on the fly. But for now, if you're not good at it, you need to probably come back and replace it. Right? And the green g to the x was 3x squared. This is it. This is it. Maybe the only thing that anybody would do here is on this part right here, it's probably more common to call it 2 natural log of 3. But if this is what ended up getting written, you will absolutely get all the points. One final question, I guess, before we leave, complete this review, would be, well, no calculus student can get away without doing some logarithm problems. So if we had h of x being log base, what do I want to say? Log base, I don't know, 6. Now let me do a prime number for whatever reason. Log base 11 of x squared minus the natural log of how about 1 over 3x plus 1, because I just love to make it confusing for you. It's my job. No, of course not. My job is not to intentionally try and confuse you or make it hard. My job is to prepare you for any such functions you would see in the future that could potentially model a situation in the business world. And let me tell you, a bunch of models get written in terms of logarithms. I put them on my tests. About like the price. The price demand model. A logarithmic curve goes down like that, but it might not ever get below a certain price. I don't want to let my price go to 0 just because I'm selling a bunch more of them. Or just because there's a huge supply of them. I don't want my price to go to 0, but I'll let it approach a minimum, right? We can do that with a logarithmic function. Okay, so here I want to take this derivative of h. Well, oh boy, this is a tough one. A lot going on here. Couple of facts. Here's a couple of facts that are indispensable. Number one, the logarithm of any base, if that argument has an exponent, then that exponent can be coming down out front of the logarithm. Indispensable fact. This is not a derivative, it's just a fact about logarithms. So that's fact 1. Fact 2, I guess, here would be the change of base formula. So any logarithm with whatever base and whatever argument can instantly become a discussion about natural logarithms via the change of base formula. And with these two facts, I think we have everything we need to do these derivatives. Because I'm gonna always, like a good calculus student, spend some time trying to rewrite my function so that it is easier to deal with. Let's start with this one. Notice that fact 1 applies. So this is really 2 log base 11 of x. Okay. And then I have the natural log of this 1 over 3x plus 1. But you and I both despise the quotient rule. And we wish to always do something to not have to deal with the quotient rule. Well, you see when you look at this part right here, what you really see is some parentheses around that denominator and an exponent of 1. So I guess we'll add to our facts list here something we discussed earlier, which is that 1 over something to an exponent is just, you move it to the other side of the division bar, but you have to change the sign of the exponent. Right? Fact 3 is what I just used right here. But I'm still not finished rewriting my function just yet. Always spending ample time rewriting the function so that it is easy to deal with. This minus 1 is now an exponent. It can come down here. I'll be. The minus 1 can come down out front, and it would be a minus of a negative, so that will be positive. So this is going to be a plus sign. It's going to be plus the natural log of 3x plus 1. Awesome. And then this part here, the log base 11 of x, that's a change of base formula. So you will have 2 times the natural log of x over the natural log of 11. Great. Wonderful. This is h of x. Are we finished? Well, I would like you to view it one more distinct way. This is not your function. Your function is here. Your constant is down there. Natural log of 11 is a constant. You should be looking at this thing like it is this constant, 2 over the natural log of 11. Here's my constant, 2 over natural log of 11, times this function, natural log of x. It's a constant times a function. And then I have this other function, natural log of 3x plus 1. This guy would need a chain rule. This guy don't need squat. We know the natural log of x. Natural log of x is 1 over x. I'm ready to write h prime. H prime of x is going to be, well, here's my constant, 2 over natural log of 11, and then times 1 over x. Great. I've done the derivatives of this part. Now it's time to differentiate term by term and do the derivative of the next part. But the next part needs a chain rule. The function on the inside is 3x plus 1, and the function on the outside is the natural log. The derivative of a natural log, so I'll say it like this. The natural log of star has derivative 1 over star. And then so it's like there's my f prime. I have to multiply it by g prime. But g prime is just the derivative of this 3x plus 1. So it's going to just be times 3. And what was star? Star is g of x. It was the natural log of star. This is 1 over 3x plus 1. Derivative's done. Derivative's done. Let's just clean it up a little bit. It's always good practice. Clean house a little bit. So I would be writing this as 2 over x natural log of 11 plus 3 over 3x plus 1. And that's my final answer. If y'all have any questions, please contact me. I want to hear from you. And good luck on this upcoming test. Bye now.